We've been using matrices to represent linear vector functions, or to think about linear vector functions, but we never really defined exactly what we mean by linear vector function. In particular, what is it that makes a vector function linear? So, a vector function is some function from a Euclidean vector space Rn to Rm, but what is it exactly that makes one of these kinds of functions linear? Let's think about, let's come at it from the point of view of matrices. So we defined, if we have an m by n matrix A, we defined a linear vector function from Rn to Rm in this way. So if you have any vector x in Rn, the way that you get a vector in Rm is you just multiply on the left by A. Right? Since x has n entries, this matrix product is defined, and the resulting vector has m entries, and so it's in Rm. But what is it that makes this linear? Well, if you take two vectors, say x and y, in Rn, and you add them together, right? This is vector addition in Rn right here. Well, if you multiply on the left by a matrix A, one thing that we know about matrix multiplication is it distributes. So this is the same thing as A times x plus A times y. And now this is addition, but remember this addition on the right, it's vector addition, but it's vector addition in Rm. Right? This was in Rn. So because matrix multiplication distributes, it turns vector addition in Rn into vector addition in Rm. Not every vector function would do that. You can imagine that most vector functions would scramble together the coordinates of x and y in a way that would make this not true. So this is actually something special about matrix multiplication. Additionally, if we take a scalar, say r, in, I guess let's call it r, in real numbers, and we took the vector r times x and multiplied that on the left by a, well, matrix multiplication and scalar multiplication associate and commute, so we could actually shuffle that scalar out in front like this. And so you see that this multiplication on the left by our matrix A has turned scalar multiplication in Rn into scalar multiplication in Rm. And again, not every vector function would do this, so this is something that's special about matrix multiplication. And these are actually the properties that we will take to define a linear vector function. And in fact, just because of historical reasons, they don't usually get called vector functions. Usually they get called linear transformations. So that's what we're going to call them. So a linear transformation is some function, any function, from Rn to Rm for some value of n and m that satisfies these two properties, or this property, if you have two vectors and some scalars, if you have r1 times v1 plus r2 times v2, when you apply the linear transformation, or the vector function t, you get the same thing as if you do r1 times t applied to v1 plus r2 times t applied to v2. Now this is really the same as the two properties that we got from matrix multiplication, because if you take r1 and r2 both equal to 1, then this turns into t times v1, or sorry, t applied to v1 plus v2 equals t applied to v1 plus t applied to v2. And if you take if you take r2 to be 0 and r1 can be anything, then this turns into t applied to r1 v1 equals r1 times t applied to v1. So you see this single property is sort of both of those things we noticed about matrix multiplication, but packaged together into one statement. So any function from Rn to Rm that satisfies this property, we will call it a linear transformation. So really these are linear vector functions, but we'll call them linear transformations because that's what everybody else does. Geometrically speaking, what's going on here is, right, if we have these two vectors, v1 and v2, and we apply t to both of them, so t does something to v1. So maybe it turns v1 into this vector over here. So this is t of v1. And t also does something to the vector v2. So maybe it stretches v2 out way like this. This picture is going to be, it's not going to fit on my sketch pad here. Let me drag this over this way a bit. Oh, this one didn't come for the ride. Okay, so suppose this second red vector is t of, come on, OneNote, t of v2. Okay, well, what makes this a linear transformation is that if you add these two vectors over in Rn, right, you add vectors geometrically by laying head to tail. So here's the sum, v1 plus v2. We could also add the results over here in Rm. So if we add these two vectors here, then what we get is t of v1 plus t of v2. And t is a linear transformation when this vector, t of v1 plus t of v2, is actually what t does to the sum. So these are equal for linear transformations. Also, there's a similar property for scalar multiplication, but the vector addition is sort of the more interesting one. So let's just check our understanding of this definition by checking to see if some functions from different Rn to Rm are actually linear transformations. So let's check this one. So we just need to take two vectors in R3 and take any arbitrary linear combination of them. When I say two vectors, I mean two general vectors. We can't actually pick vectors with numbers in them. We need our vectors to represent any vector in R3, and so the coordinates will have to be, or the entries will have to be variables. But when we have two of them, we'll just take a combination of them like this, stuff it into T, and see what comes out. Okay, so I guess for our first vector, let's use ABC. And for our second vector, let's use, how about XYZ? And now we can see what does T do to R1V1 plus R2V2. Remember, we don't know yet if this is linear, so we can't rewrite this as R1 T of V1 plus and so on, because that would be assuming that this is a linear transformation, which is what we're trying to show. So to actually compute what T does to this vector, we have to write down exactly what this vector is. So if you do the matrix or the vector operations, you get R1A plus R2X for our first entry. For our second entry, R1B plus R2Y. And then for our third entry, R1C plus R2Z. Okay, now we can compute the result of the function T, or the transformation T. The result is in R2. So the first entry is 4 times the first entry in the matrix. So 4 times this first entry, R1A plus R2X plus the second entry in our input vector, so plus R1B plus R2Y. And then the second entry in the result is 2 times the second entry in the input, so 2 times R1B plus R2Y plus, minus 3 times the last entry in the input, which is R1C plus R2Z. Okay. Now we need to compare this to R1 T of V1 plus R2 T of V2. Right? If T is really a linear transformation, then these two things are going to be the same. So let's actually compute the second one and see if we get this big mess. So let's see, R1 times T of V1. So T of V1, now we can just use the formula for T applied to this vector V. We get 4A plus B and 2B minus 3C plus, and then R2 times T of V2, so R2 times T of V2, we just use this formula again, but remember it's XYZ instead of ABC, so 4X plus Y and 2Y minus 3Z. Okay, but we can do these scalar products here, and we can do this vector addition in R2, and that gives us, let's see, R1 times these guys, so R1 times 4A plus B plus R2 times 4X plus Y, and then in our second entry we get R1 times 2B minus 3C plus R2 times 2Y minus 3Z. Okay, so are these things, this one and this one, are they the same? Well, if you look carefully and imagine distributing everything out, here's a 4R1A, there's a 4R1A, so right, those match. I'll just put a box around everything that matches. Here's an R1B, there's an R1B, so those are taken care of. Over here we have an R2 4X, here's an R2 4X, so those are taken care of. And then here's an R2Y. And there's an R2Y when you distribute that. And then for this, for this example, this also happens for the second entry. Here's a R1 2B right there. There's an two R2Y, which is right here. There's a minus 3 R1C, which is right here. And then a 3 R2Z, minus 3 R2Z, which is right here. Right, so these two things are actually exactly the same. So these are equal, and so T is a linear transformation. All right, well that's what it looks like when one of these functions is a linear transformation. What does it look like if it's not a linear transformation? Well, let's look at a couple examples. So here are a couple functions. This first one is going from R2 to R2, and the second one is going from R2 to R3. I guess a word on this notation, you might not have seen this notation before. This way of writing functions is sort of a way of writing a function without really specifying what its formula is. So this is the name of the function. The thing that shows up before the arrow, this is your domain, your possible inputs. And this thing after the arrow, this is where you end up. Now that's not necessarily the same as the range, right? The range is all the stuff you actually hit. And so some people call this the codomain. There are actually sort of two naming conventions. One naming convention is the codomain is this thing and the range is the stuff you actually hit. And then another naming convention is that this is called the range and the stuff you actually hit is called the image. So we'll stick with this naming convention for now. Okay. So this is sort of a shorthand notation for the name, domain, and codomain of a function without really specifying its formula. If you want its formula, you have to write that out separately, which is what I've done up here. Okay, so let's look at these two functions. S is going from R2 to R2. Right? S is some sort of formula that transports us from one copy of R2 to another copy of R2. Let's check if it is a linear transformation. Now, since I say check that they're not, then probably we suspect that it isn't really a linear transformation. So what would that mean? Well, that would mean that if we have two vectors and we add them and then do S, we get a different thing if we do S and then we add them, right? So sort of the shorthand for being a linear transformation is that if first you add and then you do the transformation, you get the same thing as if you do the transformation and then add, right? So maybe what we should do is just pick a couple vectors and do these two things and see if they're the same or not. So how about, I don't know, 1, 1, and I don't know, 3, 2. Okay, so let's add them. The sum of these guys is 4, 3, and S applied to 4, 3 is, just use that formula up there, 4 squared is 16, and then 3. Okay, so that's S of the sum. Now let's do S first and then the sum after. So we'll do S of 1, 1 plus S of 3, 2. Okay, well, S of 1, 1, right, we just square the first coordinate and leave the second one alone. So 1 squared is 1, and then leave 1 alone, plus, and then S of 3, 2, we'll square the 3 and leave the 2 alone. But when we add these together, we get 10, 3. And that's not the same thing as 16, 3. So S is not a linear transformation because it doesn't have this sum property that linear transformations are supposed to have. Okay, what about Y? Y looks a little more promising. Like you might have suspected that S isn't linear because, hey, look, it has a square in it. Usually things with squares turn out to be quadratic and not linear. So here's something that looks a little more promising. It looks like maybe it's linear. So let's check. Let's pick a vector and try one of the properties. Just for variety, let's pick a vector and a scalar and check the scalar multiplication property. So maybe for our vector we'll use 2, 2, and for our scalar we'll use the scalar 3. So let's check what is Y of 3 scalar product 2, 2. Well, we can do this scalar product. We get 6, 6. And then we can apply the transformation Y. So let's see, 2 times 6 minus 6, that's 6. And then 6 plus 1 is 7. And then 6 minus 2 is 4. Okay, fair enough. Now what do we get if we do the scalar multiplication after the transformation instead of before the transformation? So we're going to do 3 times, and then we'll do Y of 2, 2. So let's see, 4 minus 2 is 2, and then 2 plus 1 is 3, and then 2 minus 2 is 0. And then multiply by 3, and we get 6, 9, 0. Well, look, these aren't the same. So Y is not a linear transformation. It fails that scalar multiplication property. In fact, it also fails the vector addition property. So you can see that being a linear transformation is actually a pretty strict requirement. Most functions from Rn to Rm are not linear transformations. So this property that defines linear transformations is pretty strict. Right? But there's some compensation for it being such a strict requirement. And the compensation is that it doesn't actually take very much information to specify a linear transformation. So, for these linear transformations, these examples that we worked with, like this one right here, you might think, oh, well, that's not that much information to begin with. So, what is Sam talking about? Well, this is actually a lot of information because a formula, right? What a formula does is it tells you what the output is for every possible input, right? How much more information could you possibly have about a function other than every possible output, right? So a formula is actually a lot of information. It's actually complete information about what this linear transformation does. But for linear transformations, it's actually enough to just specify a basis. So let's suppose that we have a basis. So suppose we have a linear transformation, t, and we know what t does to a basis. So you can see we don't have a full formula for t. We only know what the linear transformation t does to this basis v1 through vn. And there has to be n vectors in this basis because it's a basis for Rn. So what does this tell us about t? Well, let's see. Suppose that we have any old vector in Rn, right? Well, since Rn is really the span of v1 through vn, and this is because v1 through vn are a basis for Rn, right? So they span Rn. So since v is in the span of these, that means v is a linear combination of v1 through vn, like this. Okay, so then the question becomes, well, what does the linear transformation do to v? Well, v is this linear combination, a1 v1 through an vn. But remember, we're assuming t is a linear transformation. We don't have a formula for it, but we're assuming that it is a linear transformation. And that means that the vector addition on the inside is actually the same as if we moved the vector additions to the outside, like this. But again, remember that t is a linear transformation, so all these scalar products on the inside we can actually turn into scalar products on the outside, like this. So a1 t of v1 plus dot 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 plus an t of vn. And these t of v1 through t of vn, we're assuming that we knew that to begin with, right? We were assuming that we knew what the transformation did only for these basis vectors. So this becomes a1 w1 plus dot 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 down to an wn. So using only our knowledge of the linear transformation on a basis, we are actually able to compute the result of the linear transformation on any vector v. All we have to do is express v as a linear combination of the basis, which is possible because it's a basis, and then use the linear transformation properties that t has. And we're able to come up with an expression for the result of the linear transformation applied to v. There's actually one slightly subtle thing here, which is what if we expressed v as a linear combination of all the other v's in a different way, right? We've seen that it is possible to have two different ways to express a vector in terms of a spanning set. But actually, that can't happen if it's a basis. So remember, one of the important properties of a basis was that for a basis, you can express a vector as a linear combination of the basis in only one way. So when I suggested that maybe there was a different way that we could write this, there actually isn't a different way. This is the only way to express v as a linear combination of all the other v's, right? Essentially what is happening here is that the v's form a perfect coordinate system for Rn, so that for any other vector, there's only one way to write this vector as a multiple of v1 plus a multiple of v2. Right? This is what you would want from a coordinate system, that every point has a unique set of coordinates. And if we have a basis, we have exactly that sort of uniqueness of coordinates, kind of. So linear transformations are determined by their values only on a basis. So if you want to write down a linear transformation, you don't really have to write down a full-blown formula. You just have to say where a basis goes. And in fact, you only have to say where any basis goes, because as soon as you've said where a single basis goes, everything else about the linear transformation is determined completely.